In 2014, the largest ocean search in aviation history swept over 120,000 square kilometers. Yet MH370's wreckage was never found. Now, Ocean Infinity claims it can do in 55 days what governments could not. But if the world's best missed something so massive, what is about to change? And what are the risks if the data guiding this new search are still wrong? The search for MH370 began with only fragments of information. Investigators had no flight recorder signal, no distress call, and almost no radar track after the aircraft left Malaysian airspace. The main clue was a series of satellite handshakes, brief automated exchanges between the aircraft and an Inmarsat satellite. Each handshake produced two types of data: burst timing offset, which gave a rough distance from the satellite, and burst frequency offset, which hinted at the plane's speed and direction. But these were not precise coordinates. The so-called seventh arc, the final handshake, was a curve stretching across the Indian Ocean, hundreds of kilometers wide. With so little to go on, search planners relied on assumptions. The aircraft was assumed to have flown straight. The engines were assumed to have run until fuel exhaustion, and debris was assumed to drift west on ocean currents. But every assumption added uncertainty. As the search ships set out, the southern Indian Ocean revealed its own challenges. The seabed in the high probability zone is anything but flat. Broken Ridge and the Diamantina Escarpment cut the ocean floor with steep slopes, deep troughs, and sharp ridges. Surface-towed sonar, the main tool at the time, worked best on level ground.
If you want more stories like this, like and subscribe. Your support helps us investigate the stories that still need answers.
When pulled behind a ship, its acoustic beams swept wide, but could not see behind underwater hills or into deep canyons. Any object, an engine, a wing, the fuselage itself could lie hidden in the acoustic shadow of a ridge, invisible to the sensors above. Investigators from the Australian Transport Safety Bureau and Inmarsat analysts later traced these gaps with sobering clarity. In some sectors, entire strips of seafloor fell into blind zones. Even with 120,000 square kilometers scanned, the search left behind pockets of uncertainty, places where the wreckage could have rested, undetected, just out of view. Ocean Infinity's approach begins where cables and surface-towed gear reach their limits. Their search fleet relies on autonomous, underwater vehicles, untethered, battery-powered robots designed to operate at depths greater than 6,000 meters. This depth rating is not just a technical milestone. In the southern Indian Ocean, the seafloor plunges well past 5,000 meters, with steep escarpments and deep troughs that challenge even the most advanced equipment. Unlike traditional towed sonar, these autonomous underwater vehicles are not dragged behind a ship. Each vehicle is programmed to navigate the rugged terrain independently, following precise routes mapped before deployment. On board, they carry a suite of high-resolution sensors, synthetic aperture sonar for detailed imaging, multi-beam echo sounders to map contours, sub-bottom profilers to see beneath the sediment, and high-definition cameras for close-up inspection. All this data is processed in real time within the vehicle, allowing immediate detection of anomalies, with no need to wait for the robot to surface. Dr. Emily Carter, a marine robotics specialist, describes the advantage this way. These vehicles can move in and out of canyons, hug the seafloor, and overlap their scans. That means fewer blind spots and a much higher chance of spotting debris, even in the most complex terrain. Ocean Infinity, Chief Executive Officer Oliver Plunkett adds this: "We are not searching with one pair of eyes. We are searching with a fleet of robots, each one able to see what the others might miss." This level of autonomy and sensor integration is what gives Ocean Infinity confidence for the search ahead, covering ground faster, seeing deeper, and minimizing the gaps that haunted earlier missions. The countdown begins as Ocean Infinity's vessels reach the refined 15,000 square kilometer search zone. Before a single sweep can start, engineers and technicians focus on calibration, a process that determines whether every scan, ping, and image will be trustworthy. In the ship's control room, the team runs a series of sound speed profiles, lowering instruments through the water column to measure how temperature, salinity, and pressure affect sonar signals at depths beyond 5,000 meters. These readings are critical. Even small errors in sound speed can distort sonar images, turning a real object into a blur or hiding it completely. Each autonomous underwater vehicle is then checked for inertial navigation alignment. Onboard gyros and accelerometers are synchronized and compared with global positioning system fixes at the surface, and then pitted against acoustic beacons from the ship. This routine is not a formality. At these depths, a drift of just a few meters in navigation can mean the difference between imaging a debris field and missing it entirely. Engineers also run calibration lines, short controlled missions to verify that multi-beam echo sounders, synthetic aperture sonar, and sub-bottom profilers are all recording data in perfect sync. Only after these systems confirm precise alignment does the 55-day clock truly start. Every adjustment, every double check, is an investment in the reliability of the search. Precision here is not about speed. It is about making sure that when the autonomous underwater vehicles begin their systematic sweeps, every pixel and every coordinate can be trusted, no matter how rough the terrain below. With calibration complete, the operation moves into its most demanding phase. Up to 8 autonomous underwater vehicles sweep the search zone in parallel, each following a pre-programmed route that overlaps with its neighbors. This overlap is deliberate. In the rugged terrain of the southern Indian Ocean, a single pass is not enough. Steep ridges and deep troughs can hide objects from one angle, but reveal them from another. By layering sweeps, the team reduces the chance of missing even the smallest debris field. Every autonomous underwater vehicle collects high-resolution sonar images, multi-beam bathymetry, and sub-bottom profiles, transmitting data back to the ship at intervals. Analysts on board and onshore review the incoming streams in near real time. They look for signatures that stand out from the natural seabed, a metallic reflection, a geometric shape, the outline of an engine or a wing section. When a possible target is detected, the system flags it for further investigation. Verification begins with a second pass. The vehicle is retasked to scan the anomaly from a different direction, using both sonar and, when possible, high-definition cameras. Only if the signature persists, matching the size, shape, and material expected from aircraft components, does it move up the review ladder. Some targets are ruled out quickly, as rock outcrops or old shipwrecks. Others require more detailed analysis, sometimes drawing on forensic databases of known aircraft parts. Throughout the 55-day window, progress depends on the sea. Weather and currents can force pauses or reroute missions, but the core principle remains. Every sweep is cross-checked. Every anomaly is challenged. The aim is not just to cover ground, but to build a chain of confidence so that if wreckage is found, there can be no doubt about what it is or where it lies. A single piece of debris can be enough to solve the question that has haunted the world for more than a decade. Forensic standards set by air accident investigators require more than a sonar image or a blurry outline. Confirmation depends on physical evidence, a component that can be traced back to MH370 by unique part numbers, manufacturing marks, or layers of paint. In 2015, a flaperon found on Reunion Island was matched to the missing Boeing 777 by its serial number and construction details, verified in a French laboratory under the supervision of the BEA. The process left no room for doubt. Each stage was documented, photographed, and secured, establishing a chain of custody from the beach to the forensic bench. If Ocean Infinity's search uncovers a similar component on the seabed, the same protocols would apply. A single confirmed part, identified, documented, and matched, would be enough to declare the search a success. The threshold is high, but the standard is absolute. No matter how advanced the technology, the search for MH370 remains hostage to its starting assumptions. Dr. David Griffin, an oceanographer with CSIRO, describes the challenge this way: all our models are only as good as the data we feed them. 3 key inputs define the search box: the satellite handshake arcs, predictions of how debris drifts on wind and currents, and estimates of the plane's final trajectory. Each carries its own uncertainty. The satellite data outline a possible path, but leave a corridor hundreds of kilometers wide. Drift models use the flaperon's journey to Reunion, but small changes in windage or timing can move the probable crash zone by tens of kilometers. Even the final trajectory, whether the aircraft glided or spiraled down, remains uncertain. If any of these are wrong, the refined 15,000 square kilometer box may be in the wrong place. Precision matters, but only if the box truly holds the answer. 12 years on, families and experts still wait for certainty, not just answers. As private technology outpaces governments, the search for MH370 becomes a test of both innovation and hope. In deep water, closure is measured in evidence, not time. The search continues. Share your thoughts below.